Okay, today is May 26th, Thursday. Right now, I'm in the lab. Remember, in the back of the building where we have the offices, the faculty have the offices. I'm in there. We call it PROCE. That's the name of this lab, PROCE. Today we're going to do two things. First, we're going to start with chapter 2. Okay, so we spent 3 sessions. We can have reviewing material that you already know. If you do not understand something about chapter 1, that means that you have to go back to your class notes in solid mechanics and review it. That's prerequisite of this class. So I spent some hours, 3-4 hours, just reviewing what you were supposed to bring from the previous class. So that's all what I'm going to do about that. So let's start a new chapter. I also asked you to review the video on the principles, the main ideas about what we are going to be explaining today. And that's that if we'll see in a minute, if we analyze a piece of the beam, what happens on one end is different with what happens in the other, okay? And this difference in axial behavior is the one that forces us to include the shear stress in order to have one piece in equilibrium. That's the whole idea, okay? So that's the first thing I would like to do. So we're going to deduce an expression for what we call the shear flow. Sometimes you get a little bit confused. Flow, but this is not hydrodynamics. I know. There is some parallelism, and that's the reason, because people call it shear flow. And in the last part of the class, probably about 15-20 minutes, I'm going to see if there is any problem with the assignment. Assignment 1, which is due next Wednesday, I think, or something like that. So if there is any problem with that, I'm trying to answer your concerns. Okay, that's the agenda for today. So let's go to this. Okay. Can you see my full screen, Misayo?
No yet, doctor.
Yet, okay, so let's see. Oh, now?
Yes, doctor.
Okay, so this is the 4 topics that we are going to be reviewing in this chapter, okay? Today, we're going to cover this one here, and the shear flow, that's the term. Then, in the next session, we are going to consider the equilibrium. And through that equilibrium, we're going to deduce a formula, an expression for shear stress. And you will see that these shear stresses, they generate a distortion of the section. And that's a big problem, because when we work the first 2 sub-chapters, we're going to use some expressions from the pure bending theory, which says that the section is straight after bending. But now here we have to accept that there is some distortion. So this fact that we start assuming that the section rotates but keeps straight, but now we have to accept that there is some distortion. That's what people don't like too much. But still, the formulation that we have deduced here in this chapter, they have a lot of engineering application. Okay, that means that they are not absolutely precise, but they give us a very good approximation of what we see in the lab. Okay, and at the end, we're going to see that these distortions, these changes generated because we have to include the shear, causes this redistribution of the stresses, for example, in the flange or in the deck of a ship hull. Okay, and that will force us to try to determine the maximum stress, even though all of these points on the deck, for example, are at the same distance, vertical distance from the neutral axis. Okay, so and we do that using this concept. Oh man, I forgot to translate. It's effective breadth of the flange. Okay, so more or less that's the idea for this chapter. Okay, let's go on. So we're going to consider that when we have shear force, that's something which is very interesting. Okay, people. Only if we have shear force, we're going to have this axial imbalance. Okay, don't forget that. If you have and we can reproduce that in the lab. If we have a situation where you do not have shear force, okay, then this axial balance does not exist. And you will see that in a minute, okay? So, there. So we start by saying, okay, we're going to consider one beam which is under lateral loads and is also in equilibrium. I should say here in static equilibrium. Static equilibrium. Okay. Just to be precise. Okay, now, what's this? Okay, here you can identify the axis X. So this is axis X. Let me draw stronger. This is X. Why I say this? Because I was reading your comments, okay, in the aula virtual, and there are some confusion about the directions, okay? This is X-axis of the beam. In the vertical direction, we have Y. This is the Y direction. And of course, X cross Y give you Z. So Z is perpendicular to the X and Y. So this is the Z direction. Now, if we have some vertical load of any kind, for example, we have this, we have that, this is P of X, right? If we make a cut here in this section, we have a bending moment, okay? And if we make another cut at X position, the bending moment is M. I mean, this is very small. So this is M. And in here, we're going to have the bending moment here, but we're going to have a change. This change is what generates all of this, the need to study this chapter. Okay, if there were not this change, then we would need chapter 2. But in the general case, analyzing beams, we have this term. So we need to study the effect of shear in our beam. Okay, so that's the situation. Now, we're going to do a zoom right now, okay? Again, you can see here, unfortunately, I forgot to translate. This is in Spanish. So in this direction, this is the X direction. In the vertical direction, this is Y. And here, we're going to consider a certain cut. And the cut is located at the vertical distance Y, okay? So we have this cut located at position Y. So we have this cut at this position. It would be a line FG, okay? Now, if we consider this this cross section, this height is a differential height. So this is dy, right? If dy, it's a differential amount, it's very small. That means that the stress, okay, from G to H doesn't change much. So we're going to consider that in this rectangle, in the vertical direction, there is no change in sigma. Why? Because dy is so small, okay? Another thing is that even though you see that the width of this beam is very large, okay? This width, this dimension is very large. But in general, we're going to consider that this width is very small, right? Usually our sections are composed of plating. So if you make a cut and you consider the thickness is usually very, very small, okay? Why do we do this? Well, right now, there is no problem, but we have to consider that in a minute, okay? So after these simplifications, we can say that on this cross rectangle, see, in this cross rectangle, the stress, the normal stress is constant. And its value, you have it here, is called sigma, okay? So if we have this stress, which is constant over this rectangle in the cross section that I just presented here, I multiplied it by this differential of area. The result, of course, is force. I guess I'm missing here the subindex. So I'm considering the sigma in the x direction only. Okay. Now, remember, in this section, we have a bending moment acting. So this distribution of sigma is statically equivalent to the bending moment. And also, if you integrate the sigma over the whole section, the net axial force has to be zero because, as I said here, there is only lateral loads. There is no axial forces on the beam. Okay, let's go on. Now I'm going to work in what we call a sector. Okay, a sector starts at the cut Y, and we will go on up until the end of the section. Okay, and why is that? Well, right now I'm just going to give you a short explanation, but on Friday we will have to deduce the formula for the shear stress, and then you will see the need that starts at Y, and we will have to go to integrate to define this sector until another cut where we know the value of the shear stress. So let me write this thing here. Sector, it starts at Y and goes up till another cut where we know the shear stress. Okay, now if we take a quick look at this point, okay, at the top of the section, okay, question for you people, question for you. If I consider this stress, shear stress, okay, the top, what are the subindexes of this? Mr. Carranza, can you help me? What are the subindexes of this sigma?
It's Y.
Okay, so this is just a, I'm going to write it up here. Let me change the color because this is something that we should worry about. Okay, so when we said tau, because this chapter is about shear stress, we have two sub-indices. Let's call it I and J, okay? And the first one is perpendicular to the cut. And then this one here is the direction of the stress, okay? So you see, it's in red because we have to agree on this convention. Okay, in some cases you can go the other way. Now let's go back to Mr. Fuertes. Now, if I plot this tau at the top of the section, the direction, the vertical direction is what? What's the vertical direction? How do we call the vertical direction, Mr. Fuertes? Mr. Fuertes, are you with me?
Wait.
I can hear you. The vertical direction is here, it's Y. And we're making a cut because we're considering the top of the section. So we're making a cut perpendicular to the Y axis. Okay, so that means that this is the first sub-index is Y. And you see that it is pointing in the X direction. That means that the second sub-index is X. So on the top, this is YX. Question, if I analyze this stress, what would be the indexes for this one here? At the top, but on the cut, it will be what? Miss Aviles, it will be what?
Doctor, what cut?
The second cut, the second arrow that I just draw.
It's the horizontal cut. No, sorry.
It's the cut perpendicular to the X-axis.
Okay, is tau YX. Sorry, XY.
Yes. If you get confused, that's
Yeah.
so it's a good idea that everybody practice.
Yes,
Yeah,
because
so the first one is perpendicular to the X-axis. Okay, so the first sub-index here has to be X. So the first one, if and where am I? So the first one, Jesus Christ. Damn. Shoot. Let me stop. People, can you see my screen now? Full screen again?
Yes, doctor.
Oh man, I have problems with my whatever. Jesus Christ. Okay, so this cut here, let's see if I can still, I cannot write. Shoot. This cut here has subindices X and Y. Okay, so you see that it is perpendicular to the axis X, that's the cut, and it points in the vertical direction. So that's X and Y. Now, this YX is on the top of the section. So automatically, we can say that the stress on the top has to be equal to 0 because it's open. Okay, so this one here is 0 because it's open. All of this surface is open. Okay, and you will see that we start the sector here and we end up here. Okay, so what we're going to do is we are going to integrate this differential force over the whole sector. Okay, so this is this expression. So we integrate this force, differential force, from this cut FG until the top, where we know that the shear stress is 0. Okay, so in this case, this is in green, that's the sector where we're going to obtain this force. But now we replace the expression that we have from our previous chapter. So all of this, please be careful with this sign, negative sign here. This is what we call sigma. And remember that this comes from the assumption that the plane section keeps straight, keeps plane. Okay, so this is the bending moment. This is the cut, because we are doing a different analysis here. This is the inertia, and this is the differential area. Now, since we are analyzing this cut at X, so this value of the bending moment, it's a value for the whole section. So if we don't change X, this is not going to change. The inertia is also constant because we are considering prismatic beams. So these two terms come out of the integral, and this is what we obtain. Negative bending moment, inertia, and we have this. And this, you remember, is the first moment of the area sector. And we're going to use a very specific letter to specify this parameter. And we're going to call it Q. In this case, Q of Y. Okay, so please be careful. This is big Q. Mr. Dominguez, what are the units of Q of Y? Mr. Dominguez, Q of Y, what units does this have?
A cube.
Yeah. Now, Mr. Vasquez, what are the units of Q? Look at the formula. Mr. Vasquez.
It's gonna be newtons.
Come on, man. Look at there. You have here, you have Y. What are the units of Y? Ms. Valdez, what are the units of Y? Ms. Valdez.
Length.
Length. What are the units of dA?
length square.
Don't doubt it. So this is length cubed. So the first moment of the area, big Q, has units of length cube. Okay, we have to be careful because we are going to be working with this, believe me, very often. Oh, man. Jesus. Okay. Now, usually, we need to calculate this very, very often. So instead of having this, probably you will remember, we're going to express this in this way. This is going to be equal to the area of the sector, and that depends on y, of course. Okay, if we make a cut in a lower position or in the higher position, this area is going to change. And then we multiply that by the position of the centroid of the sector. Please, this is the centroid of the sector. We're going to practice this in a minute with a very simple section, okay? So instead of this, we're going to say Fs is going to be minus m, the bending moment, times q, big Q, and divided by the inertia. Okay, so let's go on. Now we're going to see the same figure, but from the side, because we want to check the axial imbalance. Remember the title of this subchapter. It says axial imbalance. So in the axial direction, we're going to see that we have problems with the equilibrium so far. Okay, so that's what we're going to be doing. Okay, now here I have, let me write again the axis. Okay, so axis X will be pointing to the right. This is X. In the vertical direction, this is Y. And coming out of the figure, that's Z. Okay, and here immediately, I forgot to write, but you can see that this is Y. So that's the beginning of the sector. Let me go back. Here, you see that it starts here, and then we go up. So the Y defines the position where we have the beginning of the sector. So this little piece, that's the projection of our sector. Now comes the most interesting part. Okay, on this cut at position X, we have a bending moment here. This is M bending moment at position X. And this is a different cut. Okay, there is a distance from here to there. It's a small distance, but it's different. So on this section, we have a different bending moment, and we call it MZ, and there's going to be a small change. And that's the origin of all of this problem, because this is different than that. So these forces on the sector in the axial direction, are not the same. So let's include the expression that we obtained for this force. So Fs is here. This is something that we obtained in the previous slide, minus bending moment divided by the inertia and times the Q. That's the first moment of the area sector. Okay, so this is this expression here for this, and also for that. Immediately, we see that this points to the right because this is a positive phase, and this Fs points to the left because this is a negative phase. So this will cancel that one. And this is the imbalance that we're interested in. Now, how do you evaluate this? Well, this is a differential, and it is obtained when you go from this cut to this one here. So you move in the x direction. So this differential is equal to the derivative of f in the x direction multiplied by dx. And that's the origin of all of this. So here I have, oh man, let me erase a little bit to avoid. So let me erase this. You know that here I had a, okay? So the differential, this little guy here, is equal to the derivative with respect to x times dx. Now you can say, oh, hey, wait a minute, but I could also change a difference in y. But remember that the sector here is the same as here. So the y has no change. The sector on this cut is the same as the sector in this one here. So there is no change in y, there is no change in z. The only change is because we are moving from position x to position x plus dx. So that's why we consider only the derivative in the x direction and multiply by dx. Mis puertas. How can you say which one of these terms are going to be affected by the differentiation here? Mis puertas. Which one of these terms are going to be affected by this differentiation? Mis puertas.
The moment.
Only the moment. And what's the derivative of the moment? Mis puertas. Of the bending moment. Mr. Chin Chin, what's the derivative of the bending moment?
Minus shear force.
Yes. You see? And we're saying is that this differential in force, which is the cause of this problem, is related to the shear force. So when we have null shear force, dF is going to be 0. So when we have constant bending moment, no shear force, no need for this imbalance analysis, okay? Unfortunately, we have plenty of shear forces in our beams. That's why we need to do this analysis, okay? So let's go on. So dF dx, so this term here not depend on x. Remember, the sector here and the sector here are the same. So this area and this position of the centroid are the same. The inertia is constant for the whole beam, so we can take them out of the differentiation. And this is the only term which is affected by the differentiation. And as Mr. Chin Chin reminds, this derivative is equal to minus the shear force. And since we have another negative here, this is the expression that we have. Okay? Mr. Nieto, what are the units of big Q? Mr. Nieto, what are units of big Q? Big Q. Nieto, big Q. Is Jurado, what are the units of big Q? This is the first moment. Ms. Jurado, what are the units of big Q? No? Mr. Mendez? Mr. Mendez, can you hear me?
Yes, doctor.
Big Q, big Q.
Big Q. We need
What is big Q? What is big Q, Mr. Mendez? Now, Ms. Flores, what is big Q? Ms. Flores, what is big Q? You just said it in the previous slide.
Length to 3.
Exactly, length to the third. Yes, so it's the first moment of the area sector. Here, what is this, Mr. Gomez? What is this? Big V. What is this? What is big V? Big,
Force.
What is this? V?
E, force.
Shear
Newton.
force, so units of force. Thank you. And you, Mr. Chikaisa, what are units of inertia? Sectional inertia.
Initial L
To
3,
what
right?
power? What power?
Power 3 or 4. I don't know.
No, power 4.
4, right?
Power 4. So you combine, I have 3 here, I have 4 here, and the result is F over L. And you see here, that's the ratio of change of the force when you go from section X to the next one. So it makes sense that the units are F over L. See, remember, every time you have to check the units, every time you have to check the units, okay? So this is the ratio of change of the force, axial force applied on a sector when you go from one cut to the next one. And this is what we call shear flow. Okay, now, of course, many books have different notation. In this class, we're going to call it Q. Little q. So little q is shear flow, and that depends when you do the cut. We will see that in a minute, okay? And it means shear flow, and this is the ratio of change of the force when you go from this cut to the next one on the same sector. That's very important. See, we consider a sector here, the same sector here, but you move in the x direction. Okay, so as you move in the x direction, how much does this force changes? Okay, in the moment we have this value different than 0, we're in trouble, because we are saying that we have this force and we have a different force to the right. How would you do in order to solve this problem? Because this is part of a beam, and we started saying that this beam is in static equilibrium. And the only way that we have to do in order to solve this imbalance is to include a shear force, a shear stress. That it's going to be in the next, not now, but in the next class, okay? So in the next class, we're going to include in here, if I can find my pointer, what is my pointer? Here, we're going to include here a tau. In this case, what would be the sub-indices of this tau? Mr. Carrier, what are units of this tau? Let's practice this. This will be tau what?
YX.
YX, yes. So it's perpendicular to the axis X, the cut, and you see that it is pointing in the X direction. So it's YX. So this is going to be the result of this imbalance. Okay? So, Isaga, are you there, Isaga?
Yes, doctor.
I forgot where you are. Okay, tell me. Would you please tell me if somebody, you go by the street, right? And somebody asks, Ingeniero, what's the reason? Why do we have to analyze shear stress in beams? What would you tell him?
For me, is because we have to know what if the deformation of the beam.
No. See,
how the force
what I'm trying to do
interacts
here,
between.
please listen to me. What I'm trying to do right now is that you give us like a summary of what I have just tried to explain. That's all. Mr. Romero, Chandri Romero, would you please explain why do we need to include in our analysis this shear stress, or how this shear stress appear? Mr. Romero?
Is
shear force stress is necessary to apply same force and the code the same directions for the equal two force, and only difference is the directions.
But the thing is this, I have a problem here. When you say force, I have many forces here. Mr. Chiriboga, would you please help me?
Good morning, doctor. The flexion force and the compression force.
No, come on. Miss Tapia, can you help me? Can you say, how can you summarize what I've been trying to explain to you all this morning? How do we get into the need of including the shear stress in our analysis? Let me help you. When you consider two sections in a beam, go on. Now, Mr. Soria, would you help me? When you consider two sections in a beam or two sectors in a beam, go on, Mr. Soria. Don't make me waste time, people, come on. Ms. Santos, would you please help me?
Okay, maybe the difference between the bending stresses in one section to another section along the beam are the reason for the shear force arise.
There you go. And what's the reason that we can expect to have different stress here and here, normal stress here and here? What's the reason?
Can you
I
repeat?
think it's for the height.
No, it's not.
What is the
height.
reason for you have what?
You mentioned, you said that you can have difference in normal stresses in here and also here. And I ask you, what is the reason to have this difference in normal stresses here and here? What's the reason of that?
The distance of the...
No. Miss Sanchez, what's the reason of having different normal stress in this sector than in this one here? What's the reason?
Mm,
No?
no, doctor.
No. The reason is the
Because-
bending moment, the difference in bending moment. See, if this bending moment is different than this one here, the normal stress in here is different than this one. If these two were the same, this force, this dF would be 0. This would be equal to that, and we would now need tau yx. Only if we have this difference in bending moment, we need to include the shear stress. And this difference in bending moment is because we have shear force. Okay? Mr. Dominguez, do we have a question? Mr. Dominguez?
Yes, I can see your mouse, your cursor.
Okay, but can you hear my explanation? That's what is more important.
Yes.
Okay, so right now, if we want to apply this relation, we have reviewed in the previous chapter how can we obtain a distribution of shear force, V of x, right? We obtain that using our equation of equilibrium, but combine it with the kinematic hypothesis in order to be able to solve for any type of problems, of beam problems, okay? Not only determinate, but also indeterminate. That's for V. The inertia, we have to integrate over the whole section, right? So we do this, we apply the theorem of parallel axis, right? Twice and all of that. So the only term that we need to worry about right now is Q, big Q of Y. Okay, so that's the first moment. So when we return, or we can do a short explanation, we can go on and try to see how can we make this calculation a little bit easier for us. Okay, so let's go on with this before we go to the break. So here, we're going to review how to calculate Q. Okay, so please, this is the beam like that. Okay, so this is X direction. In the vertical, this is Y direction, and in this direction is Z. Okay, we define the cut for this sector at position Y, vertical position Y, measure it from the neutral axis. Okay, that's something that we did use in the last chapter. Y is measured from the neutral axis. Okay, now let's consider that the total height this section is H. Okay, and we're to consider this case, which is the simplest. The rectangular section. Now, if we want to calculate this, we can say that before this is equal to the area of the sector times Y average. So this area is this cross area. So area, this depends on Y. Anybody, can you tell me how can you calculate this area here?
B multiplied by H over 2 minus Y.
So it's going to be H half, go on,
Minus Y.
Minus Y times
B.
Yeah. So this is half of the height of the section. Y, you see here, Y influences the area, okay? And the width is constant because this is a rectangle in here. Now, let's go with the position of the centroid of the sector, okay? So we measure from centroid is here. So how much is from here to here? This is Y average. Mr. Ramirez, how much is this? Mr. Ramirez, please. How do you calculate Y average? So the distance from here until here. Oh, this is geometry, people, come on. Mr. Llanos, what is Y average?
Good morning, doctor. Maybe H over 2.
Okay, H over 2.
Minus Y.
I don't know. Did you tell me? Miss Leon, how do you calculate Y average of this position, to calculate this position? This is simple geometry, people. Come on.
It's minus Y over 2.
I didn't get it, but people, please, if this is the
minus Y plus
uniform, plus
plus
one.
Y plus
Y
Plus Y and what?
over 2.
So yes. So basically, this is the average between this and that heights. The average of those two, that's the position of the centroid for this little rectangle. Okay, now if we multiply both, here I have the sum, I have the difference. So Q of y is going to be b over 2, and then we have the square of the first one, so it's going to be h over 2 squared minus y squared. Okay, so it's b over 2 half h squared minus y squared. What is the maximum of this function? Where is the maximum of value of this function, people?
When
Where
y
is
is
the,
zero.
pardon me?
When y is 0.
Exactly. And where is y 0? At the neutral axis. So Q is max at neutral surface. This is very important, okay? Because this will influence the value of the shear stress. So in case of, remember, shear stress, we will always be interested in the maximum value, which is around the neutral axis, neutral surface. What was the value of the normal stress around the neutral axis? Mr. Ortega, Andres Ortega, what's the value of the normal stress around the neutral axis?
Morning, doctor. The value is 0.
Exactly. So that is something that we have to have in our mind. Around the neutral axis, normal stresses are very small or at 0, and shear stresses will be very high. So unfortunately. And finally, before we go to the break, we can make, this is typical, okay? We can make a profile, okay? This is the section. So I have H from the bottom to the top, okay? In this direction, I'm going to plot Q of Y. And in the vertical direction, of course, I'm going to plot Q. What's going to be the value? Well, here we said that we have the maximum value. What's going to be the value here? What's going to be the value here of Q in here? Miss Acuña, what's going to be the value here? Miss Acuña?
Good morning, doctor. See,
Zero.
Mr. Sawai? The value here? Mr. Sawai, don't make me waste time, people. Mr. Mendes, what's going to be the value up there? In here? No? No idea. Mr.
Maybe it
Tini?
should be 0.
Yes, it's 0. It's 0. Because up here, see, you're measuring y from here. So here, y is going to be h over 2. So you put here h over 2 squared, the difference is going to be 0. So here it's going to be 0. Similarly, down here, it's going to be 0 because we have a square. So even though y is minus h over 2, when you square it, you turn it into positive. So the ratio is going to be, or the variation is going to be a quadratic. So it's going to be something like this. So that's going to be the variation of this first moment when you go from neutral axis up and down. Okay. And remember,
Doctor, excuse me. I have a question. You say Q is 0, and that point, why?
Because here, y is equal to h over 2. So if this is the value of y is h over 2, you put h over 2 here, the square is going to be equal to that with this negative sign. this whole term will value 0. So up here, it's going to be 0. Remember, in the horizontal direction, I'm plotting Q. And in the vertical direction, the vertical axis, I'm changing Y. So that's going to be the variation of the first moment. Okay, so this is very important for us. That means that we always have to look up around the neutral axis. That's the area where the shear stresses are going to be very large in general for a beam. Okay,
Doctor,
people? Yeah.
I have a question. And this graphic is only for, or this behavior is only for this case, for rectangular section, yeah?
Would you please repeat your question, because there was some noise here.
My question was that this graphic is only for, or is the behavior only for rectangular sections?
Yes, for rectangular sections. But in general, you're going to see that every time we have any section around the neutral axis, we're going to have the largest value of Q.
For example, if we have something like a T bar or I bar, it's different.
Yeah, every time you have any section around the neutral axis, the Q will be larger. And it makes sense. Let me go back. Here, for example, there's a lot of, but let me draw about here. Okay. So let's consider that we have two bending moments. Okay, I'm going to have a very large bending moment here, which generates a very large stresses. And here I have a very small bending moment. These are the normal stresses. Okay. If I make a cut here, this area is much larger than this one. So I have like a force here and then a small here. Okay. If I make a cut below, okay, we have to include this area. So this is going to be this, and this is going to be much smaller. So if I go down, you see that the difference, I have to add these two. Both are larger than these two. So when you make cuts lower and lower, this difference between this and that are going to increase. That's why we can expect this value to increase as you go down. Now, what happens if we go below the neutral axis? If you make a cut here, this force will be positive. So it starts pointing to the right. And it's going to be larger in absolute value than this one. So if you consider the whole section, okay, even though you have included all of these, if you include this is going to be pointing to the right. So the difference between the two sides start decreasing. So when you go down, 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 the difference increases. You reach here, you have the maximum difference. And when you start going below the neutral axis, the difference start reversing. Okay, and that you can expect that here we have a maximum and we start decreasing. And when you go down here, see the whole force pointing to the right will be 0. And in this direction, it's going to be 0. And that's something that we did in last chapter. We integrated all of these stresses. And all of these stresses integrated were 0. And that gives us a reason to locate the origin of the system in the neutral axis. Similarly for any section. I don't know who was asking me, but did I answer your concern?
Yes, doctor. Thank you.
Okay, I'm glad. I'm glad. Sometimes I can answer, sometimes I can't. In this case, I was able. Okay, people, let's take a break. And when we return, we're going to consider another case. Okay, and you will see that it's a little bit more complex than this one. Okay, because it forces us to differentiate two regions, and we have to do this integration by with separate formulations. Okay, Miss Sayo, would you please stop the recording?